all these properties are important for when you get to doing finding integrals of things and doing them both when you're doing algebraic techniques and when you're doing graphical techniques like we just did. Second part of this chapter deals with something called the average value theorem, which is really, really important because when I was looking through AP questions to give to you guys, I couldn't give about half of them because almost everyone had a average value problem. So the stuff that I'm going to teach you tomorrow is not very hard. It's just how do you find the average value of a function, and we'll learn that tomorrow. So that's the second part of this lesson. So in any case, this is just a bunch of properties of integrals, and the first one is called the order of integration. And that just says that the integral from a to b of f of x, I think they wrote this a little bit different in your book, but I think it makes more sense this way, is equal to the negative integral from b to a of f of x dx. In other words, if this value from a, so when you integrate something, the order in which you're put these a's and b's is important. It's not arbitrary. So this means you're taking the value of the area under the curve of some function as you go from a to b. And in this case, that would be a positive number, right? If I go from b to a, meaning I take a minus b to find my width of my interval, then I would get the negative of whatever this value is. So if I switch those things around, then I'm integrating backwards, because think of it in this case, a minus b would be a negative number, right? And so I would be multiplying a negative width, more or less, times all these infinitely many heights to come up with negative areas. Now, this is not always a negative number, because if this comes out to be a negative value, then this would be a positive value, right? Is it possible for this to be a negative number? Yes, when the graph is underneath the curve. So say, for instance, I wanted the integral of this function from a to b. That would be a negative number, right? Because my y values are all negative. But my dx's are all positive, which is basically you're integrating, adding up little teeny, infinitely small chunks of area. So that's what that says. Questions about that? You can figure that. And then you're going to have applications of this. Okay, next thing is called the zero integral. Zero integral, and this is pretty kind of intuitive, but the integral from a to a of f of x dx is equal to 0. In other words, if I have some function and I'm going from, and this is point A, and this is point B, but I'm only going from A to A, right? I don't go anywhere, right? So there's no widths of rectangles to add up, right? So the area under the curve from A to A, since the width of my rectangle is 0, basically, that would be equal to 0. Eric, is that easy a question? Do I need to do an example of that or anything? But they might give you something like, that looks horrible. I might say something like, okay, find the integral from 0 to 7 of e to the, no, not from 0 to 7, from 7 to 7 of e to the x squared over natural log of x dx or something like that. And you say, I have no clue how to do that. What's the answer to that problem?
0.
That's just 0, right? So that would be like a trick question. You know, they give you something that looks horrible and you go, I don't know how to do that integral, you know, and stuff like that. And then you just, oh, it's just from 7 to 7, so I'm not going anywhere. So it's 0. Okay? Next one is called the constant multiple, which we kind of already have applied. I don't like this color anymore. Is that better? You don't care. Constant multiple? Isn't that a place in Turkey? Oh! Constant Oh, that's Constantinople. Oh, there's something like that. Okay. Constant multiple of the integral of a to b is equal to k times f of x dx. This is a k is equal to k times the integral from a to b of f of x dx. So in other words, if I have that's a k, not an h. So if I have a k inside my integral symbol, I can pull that constant outside. So for example, say I have something like find the integral from -3 to 7 of 6x squared dx. Okay? That's equal to, I can pull that 6 outside, so that's equal to 6 times the integral of x squared dx from -3 to 7. And sometimes it's very helpful when you're doing algebraic techniques with integrals to pull that constant outside, or if they give you the value, they say, oh, the integral of x squared is from -3 to 7 is 500. Well, it would be 6x, the integral of 6x squared. Okay, so that's called the constant multiple property. Sum and difference of integrals. Let's change colors again. Sum and difference. Sum and difference say that if you have an integral from a to b of f of x, I'm going to put parentheses there, plus g of x dx, okay, that's equal to a plus or a minus. So I could have a minus sign there too. That's equal to the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. And sometimes that's useful in evaluating integrals as well. So say, for instance, that you want the integral, which we did the other day, right, from -pi to, let's say to 2 pi of sine of x plus cosine x dx, right? Well, it'd probably be better to break that into two separate integrals like this, sine of x dx, which you could probably do now because we told you what that integral is, -pi to 2 pi of cosine of x dx. All right, so that's what this property says. You could break apart an integral which is a sum into the sum of two integrals over the same interval. Okay? Questions? Easy? Okay. The next one seems like the same thing, but it's not. Okay? So this is called additivity. I didn't know this was a word, but apparently it is. Additivity. And what this says is that if I have an integral from a to b of f of x dx plus the integral from b to c of the same function f of x dx, that's equal to the integral from a to c of f of x dx. And you say, oh, that looks just like what I just showed you. It's not the same thing, okay? So say, for instance, I have some function and it kind of goes like this, and then it goes like this, or something like that. And I want, say this is point A, and this is B, and this is C, right? I can, if I want the value of the entire integral from A to C, I can take the area under this curve, which would be represented by that, plus this, which would be a negative number, to get this, right? And you already kind of applied that in the previous homework. Yeah?
Yeah. It's good.
Sure. It's good, she says, Kate. Yay. Moving on. How much time do I have? 6 more minutes. One more two more properties. Okay? The max min inequality. Max min inequality. And this is the first time I saw this, but this leads to the average value theorem. Okay? If max f and min f are maximums are the maximums and minimums of f on an interval a to b. Then min f times b minus a is less than or equal to the integral from a to b of f of x dx, which is less than or equal to the max f times b minus a. What the heck does that mean? Okay? That means if I have some function, so let's just draw it in the first quadrant here. So say it goes up here, goes down here, and then it kind of ends here. Okay? So here's a starting point, here's the end point. Here's the minimum, right? This is the minimum, and this is the maximum, right? So if I take this maximum value and multiply it by b minus a, what is b minus a? It's the width of this rectangle right here. So I would get the area of this rectangle, right? So the maximum times b minus a would give you the width of this, would give you the area of this rectangle. The minimum, right, times b minus a would give you the area of this rectangle in here. You see that? Okay? The area of this so what that says is that the area of this rectangle has got to be less than the actual area under the curve. And the area under this rectangle, where the height is the maximum value over that interval, has got to be bigger than the value of the interval. Is that right? And that leads to the mean value theorem for integrals and the average value theorem, which you'll learn tomorrow. Okay? And the last thing that they have is called domination. Ooh, baby, no. Domination. That's when you get dressed up in your chains and stuff to do integrals. Okay, no, it's not. I'm just kidding. You bring your whip. Oh, this is going to be on YouTube. G of x and so on AB. Then the integral, from a to b of f of x dx is greater than the integral from a to b of g of x dx. Does that make sense? What that says, if f of x is always bigger than g of x, right? So if this is f of x, and say g of x is down here, this is g of x. And if this function is always has bigger y values than this y value, then the value of the integral over an interval, this integral is always going to be bigger than that integral. That's all that says, right? That's not any big deal. But that will be useful when you're finding areas between two functions and you have to figure out which one is bigger than the other one and you have to subtract them. Okay? All right, so that's about it. And your homework is page 294, 1 through 10, and then 46 through 48. Pretty quick. Okay? So, too short. But today's a short day, so I want to give you a short lesson. All right?